Welcome to the debate. You know, if you were building a bank vault, you wouldn't build it in a foreign country, hand the keys to a mega corporation, and just hope they never look inside simply because their vault has thicker walls. You build it on site, you control the perimeter, you establish absolute jurisdiction.
Right, but
Yet, as tech architects, when we build artificial intelligence systems today, that is exactly what we are doing with our users' data. We're just shipping it off to centralized data centers. So today, I'll be arguing that the massive leap in decentralized local hardware, specifically consumer neural processing units or NPUs, means developers can and should build off-grid sovereign AI.
and I will be taking the opposing view. Because when the threat you're facing requires a vault the size of a city block, built with materials you can't possibly source locally, you lease the fortress. You don't try to defend a cardboard box just because it sits in your living room. The physics and economics of AI make centralized compute completely inevitable.
A cardboard box, really?
Hey, I mean, compared to a data center, yes. I'll be arguing that the future of serious AI development isn't retreating to edge devices. It's architecting for highly centralized, compliant, sovereign clouds to navigate regional localization laws.
Well, the clash we are exploring today really is the defining architectural tension of the next decade for any developer listening to this. I mean, we are looking directly at the intersection of bare metal hardware advancements and the deeply contested, rapidly evolving landscape of international data law.
Oh, absolutely. It's unavoidable.
Right. So let me lay out exactly why I think the edge is winning here. True data sovereignty is only possible at the hardware level, period. We're seeing an absolute explosion of NPUs integrated directly into consumer devices right now.
Sure, the hardware is getting better.
Better is an understatement. Think about Intel's Meter Lake processors with built-in versatile processing units. Or solo builders just attaching Halo AI accelerator modules to a Raspberry Pi 5. By leveraging low bit width operations like INT4 and INT8 and utilizing local APIs, developers can build applications that shield user data entirely.
Okay, but
If the data literally never leaves the physical device, you don't need to worry about the extraterritorial overreach of state surveillance like the NSA's PRISM program or, relentless corporate data hoarding. The architecture of the future is local, private, and entirely decoupled from big tech's cloud.
I completely understand the cynicism regarding corporate data harvesting. I really do. As an architect, when you look at how aggressively data is scraped, monetized, and analyzed, it is entirely valid to be skeptical.
Yeah, it's more than valid. It's a necessity.
Fair enough. But the physics of artificial intelligence simply don't care about our privacy preferences. Centralized compute is inevitable because of the massive hardware disparities. Look, a consumer NPU is fantastic for running basic computer vision tasks or lightweight text generation. But it is competing against data center-grade hardware like the NVIDIA H100 GPU.
Sure, the H100 is powerful, but
It's packed with tens of billions of microscopic transistors, MOSFETs, operating in parallel. Or Google's TPU v4 clusters, which utilize liquid-cooled packages and massive high-bandwidth memory stacks to move data at speeds a local device can't even dream of. That is where state-of-the-art AI lives.
if you're building state-of-the-art AI, maybe.
Exactly. And because of that compute gravity, data sovereignty is actually being resolved at the nation-state level via sovereign clouds and localization laws, like the EU's GDPR or Canada's IT strategy. Developers must architect their systems for these compliant cloud environments to leverage real compute power, rather than trying to, isolate themselves off-grid.
Okay, let's dig into that compute power asymmetry, because this is where the rubber meets the road for developers. I hear the argument that we are mathematically forced into the cloud, but I think that perspective really underestimates what's happening at the edge right now.
Really? How so?
Well, solo builders are squeezing massive performance out of local silicon. It's not just basic tasks anymore.
Let's be precise about what performance means here, though. If we look at the practical limits of what an off-grid AI developer can actually achieve, we often hear about NPUs boasting massive TOPS, right? Trillions of operations per second.
Yes, the TOPS metric.
It looks great on a spec sheet, but what is a TOPS metric actually measuring in this context?
Well, for the audience, break that down. Why is TOPS potentially misleading in your view?
because TOPS is typically just measuring INT8 operations. It's 8-bit integer math. It is very low precision math. It's great for taking a pre-trained model and running basic inference where you don't need highly exact decimals.
Right.
But if you are pushing the boundaries of AI, if you are doing complex inference, fine-tuning, or anything that requires high precision, you absolutely require centralized hardware ecosystems. Amazon's AWS Trainium and Inferentia chips are designed specifically for this scale.
Yeah, they have massive memory.
Exactly. They have the memory bandwidth to hold massive models in active memory. You cannot fit a data center's memory bandwidth onto a Raspberry Pi hat. The physical pipes moving the data just aren't big enough.
I agree you can't shrink a data center pipe, obviously. But I would frame the solution entirely differently. It's not just about raw hardware specs. It's about algorithmic ingenuity. Have you considered how developers are actually hacking these hardware limitations using emulation?
You mean like the Izaki scheme?
Yes. Take the Izaki scheme, for example. I think this fundamentally shifts the math we're talking about here.
The Izaki scheme is brilliant, I'll give you that. But let's explain the mechanism for the listeners so we're grounded in the reality of what it's actually doing.
Good idea. Let's make sure everyone understands how this works. So you have these local consumer GPUs and NPUs that are extremely fast at that low-precision INT8 math you just mentioned.
Right, the lightning fast but low precision math.
Exactly. But developers need FP64, which is highly precise 64-bit floating point matrix multiplications. So the Izaki scheme takes those massive, complex, high-precision matrices and mathematically splits them apart into smaller, lower precision components.
It essentially breaks the problem down.
Yeah, it's like taking a massive, heavy puzzle, breaking it into smaller, simpler pieces, feeding them through the lightning-fast INT hardware, and then accumulating the results at the end to get your high-precision answer.
Right, it's a software workaround to trick low-precision hardware into doing high-precision math.
And it works beautifully. I mean, by emulating FP64 on hardware built for INT8, developers have demonstrated a 6x speedup over native FP64 processing on consumer GPUs.
Wait, a 6x speedup?
Yeah, the capacity is totally there. In fact, since the CUDA Toolkit 13.0 Update 2, the underlying math library, QBLAS, automatically uses this INT8 emulated FP64 if it calculates it will be faster than using the native hardware.
That is impressive optimization, sure.
So the software layer is already optimizing this away for developers. The gap between edge and cloud is shrinking through software optimization. Relying exclusively on big tech's cloud compute for AI inference is like routing your home network's local traffic through a foreign ISP simply because they own bigger servers.
I have to push back on that analogy.
It is architecturally inefficient, it adds massive latency, and it completely compromises the privacy of your users.
But routing traffic is entirely different from processing complex neural networks. An ISP just moves packets from point A to point B. An AI model actively generates outputs based on billions of parameters that need to simultaneously reside in memory.
It's still moving data through a corporate choke point.
But the emulation hacks you're talking about, and yes, the Izaki scheme is a phenomenal piece of scientific computing, but they are fundamentally workarounds for a massive hardware bottleneck. An emulated FP64 operation on a consumer device is still orders of magnitude slower than native processing on a liquid-cooled TPU v4 cluster.
Well, obviously, but
Emulation doesn't solve the memory bandwidth problem, it just optimizes the compute you actually have. That physical hardware bottleneck forces enterprise architectures into the cloud. And once you are in the cloud, you run headfirst into the real issue here, which is the jurisdictional nightmare of data sovereignty.
Which is precisely why I argue developers should avoid the cloud altogether. If you stay on bare metal edge devices, you never enter that legal minefield.
But developers building enterprise systems can't stay on the edge. The models are too big, so they have to navigate the law. Let's talk about the legal mechanics here, because it is fascinating and honestly terrifying.
It really is.
The U.S. Cloud Act allows U.S. authorities to demand data from covered service providers regardless of where that data is physically stored around the world. The courts can compel a parent company to provide data held by their foreign subsidiaries.
This creates a direct, massive legal tension with Article 48 of the GDPR, which restricts the transfer of personal data in response to foreign court orders. Think about what that means for a developer.
It's a paradox.
Yeah, as an architect, you're legally required by the EU to keep European data local, but technologically forced by compute requirements into a cloud provider that is legally required by the US to hand over data. You are architecting a literal paradox.
It's an impossible situation.
It is. But the solution to this isn't retreating to a consumer NPU, it's the sovereign cloud model. Look at Microsoft's famous legal battle from 2013 to 2016 over a Hotmail server hosted in Ireland. The US Department of Justice demanded the emails on that server. Microsoft refused, citing EU data localization laws.
Right, they fought it.
They fought it all the way up. Cloud providers will fight for localization rights because it's their business model. They are building sovereign clouds, meaning data centers physically located in specific regions, operated by local citizens to legally ring-fence your data while still giving you access to H100s and TPU clusters.
I hear the argument, but come on. The sovereign cloud is a corporate oxymoron.
An oxymoron? How?
It's a marketing term designed to pacify architects while big tech maintains a centralized monopoly over compute. You mentioned Microsoft fighting the DOJ, and sure, they push back in that specific, highly publicized instance. But let me remind you of the U.S. Patriot Act and Section 702 of the Foreign Intelligence Surveillance Act, or FISA.
Ah, the warrantless surveillance provisions.
Exactly. FISA 702 authorizes intelligence agencies to compel electronic communication service providers to assist in warrantless foreign intelligence collection. If you put your users' data on a corporate server, regardless of what region that server sits in, regardless of what sovereign sticker they put on the data center door, it is vulnerable to extraterritorial reach.
It's a risk, certainly.
Absolute sovereignty doesn't mean regional servers. Absolute sovereignty means zero data transmission.
Okay, zero data transmission is an absolute, yes. But is it a practical reality for modern intelligent applications?
It has to be. We have to architect our way out of this. And there is a profound precedent for this that goes way beyond Silicon Valley. Look at the deep roots of indigenous data sovereignty. We're talking about frameworks built by Gwen Phillips of the Katanaksa Nation in Canada, or the Timanara-Waranga Maori Data Sovereignty Network in New Zealand.
And those are important frameworks, but how do they translate to a developer's software architecture?
The core architectural principle of indigenous data sovereignty is absolute control over who accesses sensitive data and where it resides. It's not just about access controls and a cloud dashboard, it's about physical custody.
Right.
I mean, the UN General Assembly formally agreed to adopt the Declaration on the Rights of Indigenous Peoples, confirming the right to control scientific and technical data. If a community says our demographic data or our cultural knowledge cannot be processed by a foreign corporation, how does a solo developer implement that? You can't just throw it in an AWS US East bucket and promise it's safe.
No, obviously not.
You have a moral and architectural obligation to keep that user data off corporate servers entirely. Furthermore, look at Finland. Just recently, in February 2026, they launched the Digital Independence Initiative. Why? Because dependency on third-country digital infrastructure actively weakens national autonomy. Relying on a foreign cloud provider is architecting a vulnerability directly into your stack.
Look, that is a compelling philosophical argument, and I deeply respect the principles of indigenous data sovereignty and Finland's Digital Independence Initiative. Custody is vital, but we have to translate philosophy into engineering at scale. Enterprise developers cannot build global, highly intelligent products on a philosophy of complete isolationism.
I wouldn't call it isolationism. I'd call it security.
But the sovereign cloud isn't just marketing. It is a complex legal and technical framework actively being negotiated by governments. In Canada's IT strategy for 2016 to 2020, they explicitly pushed data localization measures to uphold citizens' privacy against things exactly like the Patriot Act.
And did it work?
Yes, it is messy, and yes, government entities like Shared Services Canada have had to explore hybrid options with U.S. providers, but that is the arena where the battle is actually fought and won. You build regional infrastructure.
But if you build entirely on local NPUs, you don't even have to fight the battle. The data never leaves the device. The NSA can't subpoena a piece of silicon sitting on my desk if it never connects to a centralized server.
Okay, keeping data on the device sounds great until you actually try to write the code for it. Have you looked at the hardware fragmentation out there right now?
Well, it's getting better.
If you commit to off-grid AI, you aren't just writing code once and deploying it. You are stepping into an absolute nightmare of overlapping APIs. You are targeting Apple's Core ML for iOS, Intel's OpenVINO for PCs, AMD's Ryzen AI, Qualcomm's SNPE for mobile.
I admit, the fragmentation is a headache.
It's more than a headache. It's an engineering black hole. If you're listening to this and you've ever tried to compile for Core ML and OpenVINO in the exact same development sprint, you know the exact migraine we're talking about.
Fair point.
Each of these local platforms has a different memory architecture. They support different levels of precision. They have entirely different compilation pipelines. It's like trying to hire a construction crew to build your vault, but the plumbers, the electricians, and the framers all speak completely different languages and refuse to use the same blueprints. How can solo builders realistically ship products across that landscape without burning massive amounts of engineering hours?
Historically, yes, that has been brutal.
And before you answer how we solve the API issue, let me add a macroeconomic concern here, because the isolationist approach has systemic costs. Economist Susan Ariel Aronson, director of the Digital Trade and Data Governance Hub, points out something critical.
Okay, what's her take?
Generativity. It stifles the public benefits of AI analysis. If every developer silos their application data on local NPUs, the aggregate foundational models don't improve.
Right, we lose the shared data pool.
Exactly. We lose the shared intelligence. The medical breakthroughs, the traffic optimizations, the climate models, all the stuff that makes AI so powerful in the first place.
I see the logic there, but I fundamentally disagree with the premise. Regarding the data generativity argument, protecting a user's fundamental right to privacy is infinitely more valuable than feeding a centralized corporate algorithm just to slightly optimize a global model.
Even for medical breakthroughs?
We shouldn't sacrifice personal sovereignty for generativity. The medical breakthroughs you mentioned can be achieved through federated learning, where the local NPU computes the insight and only shares the anonymized mathematical gradient, not the raw data.
Okay, fair enough. Federated learning is a valid middle ground. But what about the technical fragmentation, the API nightmare?
You are absolutely right that compiling for 4 different hardware targets has been a massive barrier. But the open source community and standardization bodies are actively dismantling that barrier as we speak. Look at the Kronos Group's 2025 standardization efforts.
Oh, I've seen some of this, yeah.
They recognize the exact problem you are describing, the massive software development effort caused by overlapping AI APIs. They are solving it at the foundational level. They are expanding data types and intrinsic operations natively within OpenCL and Vulkan. Even more importantly, they are including compute graphs in SPRV and introducing the N and EF in scriptand file formats.
Hold on, let's define SPRV for the audience because that's a critical piece of the puzzle.
Right, my bad. For those who haven't been deep in the Kronos updates, SPRV is essentially an intermediate language. Think of it like a universal translator for GPUs and accelerators.
Right.
Previously, you had to write your neural network specifically for Apple's chip and then rewrite it for Intel's chip. Now, with SPIR-V and NNEF, you can describe your neural network in a unified, standardized format. You write the application once, define the compute graph, and the open standards handle the hardware-specific translation beneath the surface.
So it abstracts away the proprietary hardware layer entirely.
Exactly. It translates your single code base so that the specific hardware underneath, whether it's an NPU, a VPU, or a mobile chip, can understand and execute it perfectly. Developers are being handed the tools to build unified off-grid AI applications without ever needing to lock themselves into a proprietary big tech cloud ecosystem.
Wow.
You don't need AWS or Google Cloud to be the universal translator anymore. The developer experience on the edge is finally catching up to the cloud.
Well, I will concede that the Kronos Group's standardizations are a massive step forward for edge compute. Abstracting away the hardware layer with SPIR-V is elegant engineering. It really solves the API migraine.
Thank you.
But abstraction doesn't generate compute cycles out of thin air. Even with perfect API unification, even with the Yazaki scheme maximizing every ounce of low-precision math, you are still physically bound by the thermal and power limits of the consumer device.
For now, sure.
For lightweight inference, sure, standardizing local NPU access is a huge win for solo developers. But when an enterprise architect needs to deploy a massive foundational model, they will still be looking at the cloud. And because they are looking at the cloud, they will still be wrangling with the paradox of the Cloud Act and GDPR.
Which brings us to the core of where we stand today, I think. For the developers and architects listening, my stance remains that the true future of AI architecture lies in your own hands, utilizing the immense power of local NPUs. Keeping data entirely on device is the only foolproof architecture against the extraterritorial reach of laws like the Cloud Act.
It's definitely the most secure route. Yeah.
And it's the only way to completely bypass corporate data harvesting. With frameworks like SPARE-V standardizing the deployment process and emulation hacks like the Osaki scheme maximizing local silicon, absolute sovereignty is not just a philosophy anymore, it is a viable engineering reality. You can build powerful AI off-grid.
And to summarize my perspective, while the edge compute ecosystem is fascinating, and off-grid AI will undoubtedly capture specific consumer niches and privacy-critical applications, it simply cannot overcome the physics of scale. The raw power of data center hardware, with its massive transistor counts and memory bandwidth, will remain the backbone of heavy-duty AI development.
Even with the legal mess?
Yes, the jurisdictional clash between U.S. data access laws and European or Canadian localization laws is messy. It's a paradox, like we said. But evolving legal frameworks around sovereign clouds are how mature enterprises will secure their data. You don't abandon the most powerful compute infrastructure in human history just because the legal framework requires careful, complex navigation.
Well, what we can both acknowledge, without a doubt, is that the intersection of bare metal hardware acceleration and international data law will be the defining challenge for tech architects in the coming decade. You can no longer separate the code you write from the geopolitical reality of where it runs.
Absolutely. There is an immense amount of value in understanding both paradigms. Whether you are hacking an INT8 NPU to run complex inference locally in your living room, or, configuring a highly compliant sovereign cloud deployment across international borders, there is so much more for developers to explore regarding AI standards and data policies.
Which brings us back to where we started. Whether you choose to lease the megacorporation's impenetrable fortress, accepting all the legal strings and surveillance attached, or whether you forge your own keys and build the vault on your own local hardware.
The most dangerous thing you can do as an architect today is to build the vault without knowing who actually owns the blueprints.
Exactly. Thank you for joining us today on The Debate.